I've got three things that I want to do today, and if I don't get to all three, it won't be the end of the world. But I'm also going to try a little bit of technological innovation. And so I have an external camera, and I'm going to try and work with it. Now, the three things I wanted to talk about.
Black screen so far, Charlie.
Yeah, we're coming. It's just slow. Okay. And so, and it's slow to respond to. See, I've picked up my pen and there it is. I'm picking up my pen on the picture. That's the kind of response time. So maybe Zoom is not the way to do what I want to do. And we will all suffer accordingly. But I want you to remember that a couple of weeks ago, I was talking about Gauss's trick. Gauss's trick for adding up an arithmetic series. And if you remember, I said he would start and he would sum up to some, well, the story was always that he had to sum from 1 to 100. That so let me just stop a minute and say, is this working? Can people see it unfold there? So he was just going to take some index I, and he was going to sum it from 1 to 100. Yeah, the latency is kind of a killer. And you know, and I showed you that, and I told you this story. And in fact, what was it? It was something like this. We said, oh, suppose you get 1, 2, 3, 4, and then up to 50, and then we've got 51, and then we go, and then I said, okay, let's go 97, 98, 99, and 100. And Gauss's trick, again, just sort of show you diagrammatically what Gauss's trick was. Gauss's trick was to match these things in pairs, kind of like what Kahn was talking about for the interference pattern. But what he said to do was take the 50 and the 51 and add them together, you know, and then do that pairwise, and you get 101. And then you do that pairwise, 97, 94. You go 3 down to there. You go 98 to there. See, there's the 3 and the 98 showing up. 99 and 2, and so on, and finally 1 and 100. And so each of these, of course, is adding up to 101. And you can see, looking at the diagram, and this was Gauss's insight as a 10-year-old student in a Prussian school, that what you've got 50 of these pairs. And so the answer is going to be 50 times 101. And I talked about that before. And actually, I can do 50 times 101 in my head, and so can most of you. And so he was able to write down this answer almost as soon as it was posed to him, as the problem was posed to him. Now, Steve asked, somebody's got to mute. Yeah, Steve asked at the end of that talk. He said, "Well, does this work in other bases than base 10 arithmetic?" And I actually, to my embarrassment later, I hesitated. But the answer is, oh yeah, definitely works. And in a way, this geometric pattern shows that it will work. The formula is, in general, well, let's see. Which is saying if you have this index and it runs from 1 up to n, the answer will always come out to be n times n plus 1 all over 2. And it does not make any difference what base you are using. The numerical value that corresponds to n, or or maybe I should say the symbols you're using for n do not change the answer. It'll come out right in any base. And as I was thinking about this, I came across what seemed to me a very pretty geometric proof of this this formula here. This is the general formula for the summation of an arithmetic series. But I like this. Let me just show it to you. Maybe you won't like it as much as I do. That's been known to happen in pedagogy before. But I'm going to do it with dots. And I don't know if you can see on this paper, I could actually turn this paper over like this. And now I have a piece of paper here, there. You see, it's got nice little squares. So I can imagine that instead of writing out the numbers, I did the dots. So suppose we were going to add 7 dots, and I put the 7 dots there. So this would be 1. But I'm going to add them up. So this is the first dot. Oh, well, let's get all the dots down there. Okay. Now I put a dot there. So that's 1 and 2. So for the next number, I have 1, 2, and 3. Then you can see how I'm going to do this. So I'll do 4 dots and 5 dots. Oh, so I didn't actually put 7 up there. I'll put up 7 now. 1, 2, 3, 4, 5, 6, 7. And what you get from this pattern is that the total sum, if I want to know the sum of the numbers of 1, 2, 3, 4, 5, 6, and 7, I just count the number of dots. But the number of dots there is pretty close to being half of the area of this square. And I'll just do it like this. So here's a square. And you can see that the number of dots there, suppose I had n dots along that side. I've got 7. And I've got n dots along there. So the total area of the square would be n squared, or 7 times 7. Now, actually, that doesn't come out quite right, because you see, what I'm doing here is I'm giving, if I take n times n and divide it by 2, I get the area of that triangle. But I'm off by a little bit, because the actual area involves these little pieces here, which is half of an individual square. And so what I've got is, I've got that the area that's occupied by these dots is n times n over 2 plus, I have to add in a half a little square for each of these little squares. And if I do that, I get this, but this is the same thing as n times n plus 1 over 2. And if you remember, that's what I said that's the general formula. So in a way, I've just shown you a nice geometric proof of this formula for summing an arithmetic.
That reminds me of the proof for the Pythagorean theorem, where it's done by picture.
Oh yeah, well, I think the Pythagorean theorem proof is more complicated and more elegant in many ways than what I'm doing here, but that's a matter of taste, I suppose. Anyway, so here it is, and just for the sake of this, let's see. If I had n equals 7, I'd have 7. Well, 7 plus 1 is 8. You divide 8 by 2 and you get 4, and 4 times 7 is that for n equals 7, the sum is equal to 28. So that's I equal 1 to 7 of I. And so that's what we were saying on the other side. And you see, all right, so that's kind of nice proof, and I'll just go back over to the other side here, because I want to talk about something else. So the question that Steve asked originally was, what about other bases? And so I wanted to talk about other bases, and this is what, Coles to Newcastle. I mean, a lot of what I'm about to say is absolutely old hat to anybody who has done computer science, computer programming, because you all know that there are other bases because you live and die in the base 2 number system. But for those of you who don't know that much about the bases,
Although I would say that any recent computer science graduate probably doesn't have a clue as to any of that.
Well, John,
we did, because we had to understand it back 60 years ago.
Well, maybe you're right, John. I'm a grandfather. One of my granddaughters graduated from a small college in Maryland with a degree in computer science, with a major in computer science. And at the dinner, we were celebrating her graduation, her commencement. And I said, "Oh, look, you know how to count using binary on your fingers?" And she looked at me with a very blank stare. And so I said, well, let me show you how to do it. And I'm not sure. This is something which I treasure as a method of counting on my fingers, because I learned it from reading Astounding Science Fiction, I think, a long, long time ago. Astounding Science Fiction used to have kind of in the middle a little real facts about real science or something like that. But I'll put my hand down here. Let's see. Now it takes a minute for it to show up. There it is. There's my hand. And what you have to realize is, if I were thinking about this, I would have labeled my fingers 1, 2, 4, 8, and 16 for the thumb. And then if I'm counting, if I want to know what letter is G in the alphabet, I go A. Oh yeah, I have to go slow though. I go A, and then I go B, and I pull back that little finger and put up the next finger, and then I go C, and I put up that finger. And this is, what I'm putting up is the ones and zeros of a binary number. And then I put up, and if you're doing this in a class, you always come to the 4 in binary on the fingers, and the class snickers because of course you're giving them the finger, which in Germany, if you give to a cop, will cause you to be fined seriously. You're not allowed to use the stink finger, but here we are, and now here I am. I went A. I lost my track though. I went A. I'll do it fast. A, B, C, D, E. There's E, there's F, and there's G. And so if I'm in a situation where I need to know stuff like this, I can see right away the answer is G is the 7th letter in the alphabet, because there's the 7 right there on my fingers. That's 111, which as people who know binary would understand. Anyway, she said to me, this is my granddaughter, and supporting John's insight, she said, oh, is that what that's about? And I thought, here's a computer science graduate, and she's now working as a computer programmer for a large corporation. So I hope what I taught her was useful. But you also see, you can count on the fingers of one hand, you can count up to 31. And if you're, I have to have a flat surface though, because I don't have enough I can't actually, let's see, what would this be? This is hard for me to do unless I have a surface to put it on. So there I am at 5. All right. And but I can do it nicely. So if I'm in a place where someone is saying, how many people are coming to the party? And I have my hand, I will put it on, usually on my thigh, and I will say, well, let's see, there's Alice, and there's Beth, and there's Jean, and there's Mary, and there's George, and there's Peter, and there's Peter's cousin, and then Peter's cousin's friend. And I'll just keep track of that as I go through with all my fingers. And then I'll say, I see, we got 8 people coming to this party. And then my wife will say, yeah, but you forgot me and you forgot you. And I say, oh yeah, right. And so.
Well, my cousin doesn't have a friend, Charlie.
Oh, well, that's your cousin who doesn't have a friend.
That's right.
My cousin has a friend. Okay. Anyway, so I end up with 10 people, but it's all done, it's all done with the fingers. And I think that's very lovely. But let me just remind people who don't know about bases about the glory of 0. Or I have actually a slide that I'm not going to show you, which is labeled Our Friend, the 0. And it's our friend because of its function as a placeholder in our numerical system. And it's an invention, and it's a wonderful invention. And it seems to have been invented by the Hindus in India, somewhere around the 8th century. Although, we're probably vague by a century or 2. And then the Arabs picked it up.
The Greeks didn't understand 0?
The Greeks did not understand 0. The Romans did not understand 0. You never saw a 0 Roman numeral anywhere. And,
in Monty Python, I might have.
Okay. You have different source material than I do, Peter. And so you have, so 0 comes into Europe only in about the 11th or the 12th, no, 10th or the 11th. Yeah, about the 11th century. And it comes in by way of the Arabs. I mean, the Arabs get it from the Hindus. And the Hindus end up with sort of place notation for numbers, which we call Arabic numerals. But of course, the Arabs actually got it from the Hindus. And the Arab conquest, was very extensive in Spain. And the Arabs were there and dominant for a couple of centuries. And that is the route by which the 0 as a placeholder and our basic number system, our system for calculating, comes into Europe through Al-Andalus. And I just remind you of what it does. I mean, I just think it's so cute that, you have a certain number of numerals. We have 0 and 9 numerals. So we have 10 in all. And out of that, we construct the base 10 system. And, but suppose you didn't have that many. Let's see, I'll just write down something like this. I'll write down a bunch of numbers: 0, 1, 2, 3, 4, 5, 6, 7, 8, and these will slowly show up on your screen. 10 and 11. That's probably enough. Now I can go on a ways. But you see what I've done here is I go until I run out of numerals. And then I write down a 1, and I'm going to start the sequence again. And the 0 is saying, oh, this is the 1's place, and the place to the left is the 10's place. But suppose I only had 3 numerals. Suppose I have 0, 1, 2, and then I have to do the same thing again. I say, oh, I've run out of numerals, so I'm going to write this as 1, 0. And now I can say, okay, I'm going to write 1, 1, and then I'm going to write 1, 2. And now I would be inclined to write 1, 3, except that I don't have a 3. And so I have to say, oh, all right, I have to write this as 2, 0. And then I have to go on and I can write 2, 1. Then I can write 2, 2. But I've run out of this. I have no more digits. I have to say, oh, I guess I have to say 1, 0, 0. And then 1, 0, 1, and 1, 0, 2. And so this is a set of numbers that represents the same number of objects, but the symbols are different. That is to say, 101 represents 10. And of course, an important feature of the number system here is that you see that the place value is actually a power of the base. That is, by that I mean, I'm going to go 1, 2, and then there's 3. So the second place to the left here is the 3's place, but the third place to the left is the 9's place. And so I can translate any of these numbers back to base 10 where I feel comfortable by saying, oh, look, I got 1, 9 here, and I got 2 1s there. What's 9 and 2? I'm pretty good at that. So that's my 11. And of course, I can do the same thing with base 2. And that's the one that you all know, because you go 0, 1, and then you don't have any more digits. You only got the 0 and the 1. And so you go, oh, okay, same thing here. I go 0, 1. Then I go 1, 1. Oh, now I'm out of digits again. So I go 1, 0, 0. And then I go, oh, let's see. I can add 1 to that, all right. But then I have to go 1, 1, 0, and so on. I mean, and again, you can translate these back into base 10 by looking at the powers of, in this case, 2. I mean, this is the 1's column, this is the 2's column, and this is the 2 squareds column, the 4's. Now, I'm telling you all this just because I wanted to end up doing an analysis of my my picture of the summing of all the dots.
I should remind everybody that a very good musical way of understanding what Charlie just talked about was to listen to Tom Lair's song about new math.
I'm not sure that helps you understand it, John. I think maybe it
If
shapes
you
your
like
attitude towards it. Anyway, so here I am, and and I have just gone through the effort of saying, well, here's a 1, here's a 1, 0, here's a 1, 1, and I'm going to go up here to this is 1, 1, 1, base 2, which I can indicate by putting a little subscript 2 on it, and that just keeps us in mind. So now my formula, the one that Steve asked, would it work in other bases? My formula becomes 1, 1, 1 times 1, 1, 1. I'm going to put a parenthesis around that, plus 1, divided by 1, 0. So here is, so over there to the right, you see the formula n times n plus 1 over 2. And here at left, I have just put in the values of n in binary. We're saying we're doing this for this 7 by 7 triangle here. And so I put in 1, 1, 1. Well, okay, now we have to do some arithmetic in binary. What happens when I add 1 to 1, 1, 1?
1, 0, 0, 0.
Right, nice, isn't it? So I'm going to get, but notice I'm going to get 1, 1, 1. And Peter says, great, very accurately, that I'm going to get this. And this is all divided by this. Can we divide 1, 0, 0 by 1, 0? I can do that in any base, I think. And you just do it by saying, oh, and then I have to multiply 100 times 111. And I'm going to get, so I'm going to cancel one of the zeros. That's how I would do it in a hurry. And then I'm going to get 1, 1, 1, 0, 0. And there's my answer. Well, what, but of course I don't ever know what it is. Like, so now I go back and I say, okay, there's the ones. I got no ones. There's the twos. I got no twos. But here come the fours. And here is the 8. And here is the 16. So no twos, no ones. There's my 16. Okay, no twos, no ones. So what do I add up? Well, I can do that. I get 28. And so, yes, Steve, there is a Santa Claus. Yes, Steve, you can do this in any base. And that's my contribution to the potpourri for the day.